In the last video, we saw several applications of the law of conservation of energy. In this video, we will see some more examples. An instructive example of the law of conservation of energy applies to skaters on half-pikes. Consider this puzzle. A 50-kilogram skater is at rest at the top of a 7-meter semicircular frictionless track. A. What is their velocity at the bottom of the semicircle? And B. How high can they reach on the opposite side of the semicircle? In this question, we were told that a skater starts from the top of a semicircular track, travels down to the bottom of that track, and reaches some height on the other side. We don't know exactly how tall yet. Their initial position we can call photo 1. Their lowest position would be photo 2. And whatever position they end up at on the other side, that would be photo 3. I'm going to set my origin such that at photo 2, they're at the origin. This is their lowest point. I'm going to set my origin to be there. I'm going to set upwards as positive y, and their initial height of 7 meters. I'll make a note of that here. Their mass is 50 kilograms. Their initial velocity is 0. So we're really being asked two separate questions over here. We need to examine what's happening between photo 1 and photo 2, and then between photo 2 and photo 3. So let's go ahead and solve for photo 1 to photo 2 first. Let's analyze this situation using conservation of energy. So KE1 plus PE1 plus the amount of work that comes in, the energy gained, minus the energy lost, is equal to KE2 plus PE2. Now, initially, our hero is not moving. Their velocity was 0, so that means that their kinetic energy was also 0. They do have potential energy, however, from gravity, since they are at an elevated position. The work in is going to be 0 because they don't have any forces pushing on them besides gravity. So you could make an argument for the normal force, but basically they aren't gaining energy from the normal force. There is no jetpack strapped to them or something along those lines. So work in is 0. Work out. We are ignoring friction in this question, and if this person is on a skateboard, wheels tend to have relatively low friction, so that's actually a sensible assumption to make. Is equal to KE2. They're definitely moving at this point, but PE2, they are now at the origin. They have lost all of their height, so that means that the height is going to be 0, PE2 is also going to be 0. So that means we're down to PE1 equals KE2. So, easy enough to solve. PE1 would be mgh1 is equal to KE2 is 1/2 mv2 squared. So, plug and chug. Mass, 50. G, 9.81. Height, 7, is equal to 1/2 times mass, 50, times v2 squared. Now let's go ahead and solve for all of this information. 50 times 9.81 times 7 gives us 3,433.5. And all of that's equal to 25 times v2 squared. Divide both sides by 25. 137.34. So V2 is 11.72 meters per second. So that is the size of V2. That is our hero's speed when they reach photo 2, the bottom of this half pike. Now, let's examine what would happen between photo 2 and photo 3. Again, we would start from the same place. KE2 plus PE2 plus work in minus work out equals KE3 plus PE3. Now at KE2, at photo 2, our hero is moving. We already figured out what the velocity was. So KE2 is not going to be 0. We have to keep it in there. But PE2 is going to be 0. Our hero is at the axis. They have no elevation. There's no PE2 to worry about. Work in. Again, they're not wearing a jetpack, so there's no work in. Work out. There's no friction, so we don't bother with work out. That leaves KE3 and PE3. But since we were being asked about their maximum height, that would be the peak of motion. If they have reached the peak of motion, they cannot be moving anymore. Their velocity at this point must be 0. They're not moving, so they don't have KE3. So all of this now simplifies down to KE2 is equal to PE3. Expand this out. 1/2 mv2 squared is equal to mgh3. Plug everything in. Half times the mass, 50, times v2, which was 11.72, squared, is equal to 50 times g, 9.81, times h3. So, half times 50 times 11.72 gives us 293. Sorry, that should have been 11.72 squared, so I'm just going to multiply it by 11.72 again. 3433.96. Is equal to 50 times 9.81. So 50 times 9.81 is equal to 490.5 times h3. And now we just need to solve for h3 by dividing both sides by 490.5. That gives us pretty close to 7 meters. So the maximum height they reach on the other side is 7 meters. And the maximum velocity that they had in the middle was 11.72 meters per second. Now, this second half of the calculation should come as no surprise. It's basically a mathematical mirror image of what was happening in the first half. In the first half, PE was turning into KE, and in the second half, KE was turning back into PE. Now remember what conservation of energy says. You can never create or destroy energy. You can only gain it through work, and you can only lose it through work. So if no work is done, all that has happened is an interplay of the energy, a transformation of the energy from potential to kinetic and back to potential again. So this is an example of energy changing forms. A very similar sort of example takes place when you see a pendulum moving back and forth. The same interplay between potential and kinetic energy applies to skiers. This example involves friction and requires a bit of lateral thinking to solve. A 60-kilogram skier has just started skiing down a 20-degree hill. The coefficient of kinetic friction is 0.1. They reach a final velocity of 12 meters per second at the base of the hill. What is the length of the hill? In this question, we have a skier who is traveling down a hill. Here they are at their initial position, and here they are at their final position. So this would be photo 1, and this would be photo 2. Now, we have been told that the mass of the skier is 60 kilograms. The size of this angle is 20 degrees. And the coefficient of kinetic friction is 0.1. So, what we have not been told is how tall this slope is, nor have we been told how far this person travels down the ramp. Although we could probably figure out that there must be a trigonometric relationship between the two, because this is a right triangle. So delta x is the hypotenuse of that triangle, and h will be the opposite side. That information is going to come in handy later on. The last piece of information we were told was that their velocity at point 2 was 12 meters per second, or more correctly, their speed was 12 meters per second. Now, before we go any further, let's take a look at this character as they are on the hill. This character would be subject to 3 different forces. The weight force, pointing down, the normal force, pointing at right angles, or at 90 degrees, to the surface of the hill, and the friction force, which points opposite their direction of motion. So if they're traveling down the hill, the friction force would point up the hill. And this would be kinetic friction. Now, they have only barely just started to move in photo 1. So their velocity at photo 1 is basically 0. That information will also come in handy. But to keep things simple, we are using kinetic friction throughout this entire question. We're not bothering with the fact that there was a static friction that they had to overcome. We're assuming that they are in the realm of kinetic friction at photo 1. Maybe it's a nanosecond after they started moving, but their velocity is so small that we can neglect it. Now, let us break this free body diagram into its component forces. We are going to need this in order to figure out how big the friction force is going to be. For the free body diagram, I will set my y-axis to be like this, and my x-axis to be like this. Now, if that's the case, then from this vertical line over here, the angle between the vertical line and this perpendicular here must be 20 degrees. That's the angle between the vertical line and the normal force. And likewise, the angle between weight and the y-axis. So, this component of weight, which is opposite the angle, would be weight sine of 20 degrees. And this one, which is in line with the normal force along the y-axis, is adjacent to the angle. So this is weight cos 20 degrees. Let us calculate a few of these values. The weight force will be calculated as mass times gravity. The mass was 60 times gravity of 9.81 That's 588.6. So that's the size of this weight force. The normal force, so weight, by the way, was calculated by mg. The normal force is equal to weight cos 20. We've seen this pattern over and over again in our free body diagrams for ramps. So weight cos 20 is 588.6 multiplied by the cosine of 20, which is 553.1. And finally, there would be the force of kinetic friction, which is equal to mu k multiplied by the normal force. So mu k, 0.1, times the normal force of 553.1, so the force of kinetic friction is 55.31. And this would be measured in newtons. So at this point, we've found out the sizes of all of the forces that are acting on this character. Now the reason why that's important is because a force of kinetic friction is almost certainly a dead giveaway that there's going to be some work out. So we need to find out how big that work out is, and the force of kinetic friction is required for that. Now we are finally ready to turn to conservation of energy. KE1 plus PE1 plus any energy which was gained from work minus any energy that was lost through work is equal to KE2 plus PE2. Initially, our skater or our skier is not moving. KE1 is 0. But they do have potential energy. We need to work out how much. The work in is non-existent because our skier does not have any sources of energy. But they are going to lose energy through friction, so work out is present. Finally, in photo 2, the kinetic energy is present because our skier is moving. We know their velocity of 12. But there's no potential energy because they have now reached our base level. They have now reached our axis, which I should really draw right now. Now, notice that this axis over here is drawn differently from the axes that we had for the free body diagram. Sometimes that has to happen. And that's all right as long as you have a clear understanding of what their height is going to be with respect to one position or the other. So there's no potential energy at the end. So PE1, that's mgh, minus work out is calculated as the force which causes the work out is the force of kinetic friction, times the displacement of our character is delta x, times the cosine of the angle between these two vectors. And all of that is going to be equal to 1/2 times mass times the velocity at photo 2 squared. Now, let us plug in everything that we know. The mass is 60. G is 9.81. Height is unknown. Minus. The force of kinetic friction is 55.31. We found that out over here. Times. The length of this slope is unknown. But we do know that this person is traveling down the slope, but friction is pointed up the slope. These are pointed, the force and the displacement are pointed in exactly opposite directions. So that means that we are dealing with the cosine of 180 degrees. 180 degrees means opposite directions. And all of that is equal to 1/2 times the mass of our character, 60, times their final velocity, which is 12 squared. Now, let's simplify this somewhat. 60 times 9.81 gives us 588.6, as we saw before. Minus 55.3. The cosine of 180 is -1. So that means we're taking the absolute value of -1 times 55.31 times delta x, and when we do that, we just get 55.31 times delta x. And all of this is equal to 1/2 times 60 times 12 squared, 4320. So far, so good. But now it looks like we've ended up with one equation with two different unknowns. How do we solve this? The answer is we take advantage of a bit of trigonometry that we saw right at the beginning of the question. We don't know h and we don't know delta x, but we do know that they are part of the same right triangle. Now, if I were to take this opposite side, the opposite side is going to be equal to, the length of this opposite side is equal to the length of the hypotenuse multiplied by the sine of 20 degrees. In case it's not quite clear where this relationship came from, let's write this out in a slightly different way. If I were to take the height, that is the opposite side of this 20 degree side, divided by the displacement, that's the hypotenuse of this triangle, I would get the sine of 20 degrees. Now all I have to do is multiply both sides by delta x, and that is going to give me this expression over here for h. Let's take this expression and let's plug it in for h in this equation. So that now gives us 588.6 times delta x sine of 20 degrees minus 55.31 delta x is equal to 4320. Now it's just a matter of simplification. .6 times the sine of 20 degrees gives us 201.31. So we now have 201.31 times delta x minus 55.31 times delta x is equal to 4320. 201.31 minus 55.31 gives us about 146. So as we wrap this up, we have 146 delta x equals 4320. And dividing both sides by 146, we get delta x is equal to 29.588, about 29.6. So this is the displacement of our character as they travel down the hill, 29.6 meters. So in this question, what took place was we did not know the initial height or the displacement of our character. So we made a note that there was going to be a trigonometric relationship somewhere down the line, which indeed there was. Because kinetic friction plays a major role in this question, we solved out the free body diagram and found out how big that kinetic friction was going to be, 55.31 newtons. And that 55.31 newtons appears in the term for work. Finally, we took the potential energy at photo 1, we basically subtract out the work, and we find the kinetic energy in photo 2. By applying this trigonometric relationship that we found earlier, we were able to simplify this down until finally we got an expression which was only in terms of the displacement. And thus we were able to solve for the displacement of 29.6 meters. Now let's see the reverse, a skier coasting uphill. A 75 kilogram skier coasts up a 10-degree hill to a long plateau. The plateau is 5 meters above the base of the hill. Once they reach the plateau, their speed is 6 meters per second. The coefficient of kinetic friction is 0.05. What was their initial speed at the base of the hill? In this question, a skier is traveling up a hill. Photo 1 is when they are at the base of the hill, and photo 2 is when they are at the top of the plateau. Now, interestingly enough, when they're at the top of this plateau, they are still moving. In fact, they have a velocity of 6 meters per second, or more correctly, a speed of 6 meters per second. The angle of this incline is 10 degrees. And the height of this plateau is 5 meters. We do not know what the initial velocity of our skier was. That's what we have to find out. But we do know that their mass is 75 kilograms. We know that the coefficient of kinetic friction between them and the surface of the ice is 0.05. And that's largely it. I think that's all of the information that we have been told. So now, given all of this information, we are now ready to analyze what is taking place. Now, we would need to take a look at the free body diagram for this one, because we know that there is friction, and friction is a classic indication that there's going to be work out. So we need to solve for the force of friction before we can find out how big that work out is going to be. Let us say that we examined the skier when they are exactly midway up the slope. Their free body diagram would look like this. Weight pointed down. Normal force would point at 90 degrees to the slope, so off in this direction. And finally, friction would point opposite their direction of motion. So if they're traveling up the slope, friction must point down the slope. So we have the force of kinetic friction, we have the normal force, and we have the weight force. Let's add in our axes. In a ramp, the normal force is always put, or the y-axis is always put along the normal force, and the x-axis is always put along the slope. Now we need to figure out how big that friction force is. We were told that this ramp has an inclination of 10 degrees. If this ramp had been perfectly flat, if this had been a flat and level surface, the normal force would point up. But since this is elevated by 10 degrees, that means that the normal force has gone off axis by 10 degrees. And that means that the weight force must therefore be 10 degrees away from the y-axis. We can now break the weight force into its components. This component along the y-axis would be weight times the cosine of 10 degrees, because this is adjacent to the 10 degree angle. This over here would be weight sine of 10 degrees. Now we have enough information to solve for the various forces. Let's write down what we know. Weight is equal to mass times gravity, which is equal to mass 75 times gravity 9.81, which works out to 75 times 9.81 is 735.75 newtons. That is the size of the weight force. What about the normal force? Since our character is not collapsing into the ramp, nor are they levitating from the ramp, the normal force must be equal to the y component of weight. So that would be weight cos 10 degrees, which is 735.75, multiplied by the cosine of 10 degrees, which is 724.57. So that is the size of the normal force. And last of all, the friction force. The friction force is given by mu sub k multiplied by n, which works out to 0.05 times the normal force. So 0.05 times the normal force gives us 36.23. It's equal to 36.23 newtons. Now that we have solved for the size of the friction force, we are ready to figure out what is the kinetic energy at the initial position. We will need conservation of energy to do this. KE1 plus PE1 plus energy gained from work minus energy lost through work is equal to KE2 plus PE2. Now initially our skier starts at the lowest possible point. We could consider that to be our the place from which we're going to start measuring our heights in this diagram. I'm fully aware that the y-axis over here does not point in the same direction as the y-axis here. That is allowed in work and energy questions. Sometimes it really does happen that the y-axis that you draw to find out the height does not correspond to the y-axis that you draw in the free body diagram. So we know that they're moving, so the kinetic energy must be positive. There must be some kinetic energy. But because they are on this origin, on this axis, there's no potential energy at first. Nor is there any work in, because there is no force which will add energy to our character. But there is a force that will subtract energy. That's friction. And all of that is going to be equal to their KE2, their kinetic energy up here, plus PE2, their potential energy up here. Let's expand all of this out. KE1 is 1/2 mv1 squared minus the force of friction is going to be responsible for work out, Fk, times delta x, that is the length of this ramp, which we still have to figure out, by the way, times the cosine of the angle between them. All of that's going to be equal to 1/2 mv2 squared plus mgh2. Now, let us solve for how long this slope is. The way that we do that is we know that this length over here is delta x, and we know that this side over here is the height. So if I were to take height and divide it by delta x, that would be the opposite of this 10-degree angle divided by the hypotenuse of this triangle. So I could say that height divided by delta x equals the sine of 10 degrees, or equivalently that the delta x equals height divided by sine of 10 degrees. We know that the height is 5, so 5 over sine of 10 degrees will give us 28.79. So that's the length of this slope. Now, let's plug in all the information we know. 1/2 times the mass, 75. V initial is the thing that we're looking for, minus the force of friction, 36.23. The displacement up the ramp is 28.79. Times the cosine of our hero displaces up the ramp, but the friction force is pointed down the ramp. That means that they are 180 degrees apart. All of this is equal to 1/2 times the mass times their final velocity, which was 6, squared, plus mass, 75, times g, 9.81, times the height, which was 5. It's a long equation, but it's very, very solvable. Let's go ahead and see what happens. Half of 75 is 37.5. So 37.5 times V1 squared minus 36.23 times 28.79 times the cosine of 180 gives us negative 1043.06. So if I were to take the absolute value of that, that's going to become 1043.06 is equal to half times 75 times 6 squared is 1350 plus 75 times 9.81 times 5 is 3678.75. Okay, so if I add up 1350 plus 3678.75, and then add the 1043.06 that got lost as work, I get 6071.81. That gives us 37.5 V1 squared is equal to 6071.81. Divide both sides by 37.5. That gives us 161.92 or 91. And so finally, the initial velocity is found by taking the square root of both sides. 12.72. So in this question, we had someone who was initially moving. They had kinetic energy. A classic physics puzzle is that of a roller coaster carriage falling down a ramp and entering a loop-de-loop. This puzzle combines conservation of energy with centripetal motion. Here's one version. A frictionless roller coaster track contains a long ramp that leads into a loop-de-loop with a radius of 10 meters. A 500 kilogram roller coaster carriage is initially at rest on the ramp. What minimum height must the roller coaster start from such that it completely clears the loop-de-loop? In this question, we have a roller coaster track that starts with a ramp and which includes this circular loop-de-loop. Initially, the carriage starts at the top of the ramp. It's going to travel down the ramp, it's going to enter the loop-de-loop, eventually reach this position over here, the topmost position within the loop-de-loop, and then it's going to continue traveling from there. Let us say that this position is photo 1, and this position is photo 2. I am going to set my origin as being the lowest point of the carriage in photo 2. And I'm going to set upwards as being the positive y direction. Now, the carriage at photo 1 starts from an elevated position. Let's call this h1. We have to find out what h1 is. We were told that the mass of the carriage was 100 kilograms. We were also told that the radius of this loop-de-loop was 10 meters. But we were not told what the velocity of the carriage was at the top of the loop-de-loop. So we need to figure that out before we can figure out what the kinetic energy is at this point. So first, let us try writing out what conservation of energy would look like, so we know what we're looking for. Conservation of energy tells us that the kinetic energy in part 1, in photo 1, plus the potential energy in photo 1, plus any work that comes in, or any energy that is added to the carriage through work, minus any energy which is lost from the carriage through work, is equal to the kinetic energy at photo 2 plus the potential energy at photo 2. Now, we know that initially the carriage is not moving. It starts off at rest. So there's no KE1. But there is definitely PE1 since it starts at an elevated position relative to photo 2. The carriage does not have a jetpack or any other source of energy, so there's no work in. We're ignoring friction, so there's no work out. By the way, that actually makes sense if you have an object which is on wheels. In general, something which is rolling tends to have low friction. Now, where it becomes a little bit more thorny is that we are being asked for a kinetic energy over here, but we don't know how fast this was going. So that means that we now have a second thing which is unknown. We didn't know the height, so we didn't know the PE over here. We don't know the velocity over here, so we don't know the kinetic energy either. But we can say that PE2 is going to be 0, because this object, this carriage, is now in line with our axis, with our origin. So PE2 is 0. So this whole thing now simplifies to PE1 is equal to KE2. Expand it out. M times G times H1 is equal to 1/2 times mass times the velocity 2 squared. We're looking for H1, but the problem is we don't yet know what V2 is, so we need to find that out. Let's examine this position a little bit more closely. If we were to draw the free body diagram for the carriage in this position, we were told that it was traveling at the lowest possible speed that allows it to complete the circle. And if that's the case, then this carriage is only feeling one force: weight. If you had a greater force, like for example weight plus a normal force coming from the track, then that would correspond to a higher velocity, because centripetal acceleration, the acceleration towards the center of the circle, increases as the velocity increases. So the lowest possible centripetal acceleration must correspond to the lowest possible velocity. So I'm going to set my axes with the y direction being positive, weight pointing downward. The weight force is easy to find. It's just equal to mass times gravity, which works out to 100 times 9.81, which is 981 newtons. Now that we know the weight force, we can easily solve for how big the centripetal acceleration must be. The centripetal force, which I'm drawing out here in gray, is going to include only one force, the weight force. And since we know that the weight force is 981, that means that 981 must be equal to mass times centripetal acceleration. If we want to be particularly rigorous about it, we would include the directions as well. But in this case, as in many cases regarding centripetal force, we're really only concerned about the sizes of these different quantities. So 981 is equal to the mass, 100, times the acceleration, which is what we next need to find out. Divide both sides, we get that the centripetal acceleration is equal to 9.81 meters per second squared. And that makes sense because the only force that's contributing to centripetal acceleration at this point is weight. So since the weight force creates an acceleration of 9.81, and since that is the centripetal force, you expect the centripetal acceleration to also be 9.81. But centripetal acceleration is also equal to tangential velocity squared over r. And we have been told what r is. So that means that, let's write it over here, 9.81 is equal to vt squared over r, which is 10. So now it's easy to find what the tangential velocity is. Vt is equal to 9.81 times 10 and then take the square root of that. 9.9 meters per second. So now, in this procedure over here, we have solved for how big the centripetal acceleration is going to be, and correspondingly we have solved for how big the tangential velocity must be. But the tangential velocity over here is also equal to the velocity which is there present at photo 2. So now that we've solved this, we're going to take it and we're going to plug this in for this velocity here. Taking this and inserting that information, we would get the mass, which we were told was 100 kilograms, multiplied by g, 9.81, 100 times 9.81, times the height, which is what we're looking for, is all equal to 1/2 times the mass, again 100, times the velocity, 9.9, squared. Now it's just plug and chug. So take 9.9 squared times, or let me do it this way, 0.5 times 100 times 9.9 squared gives us 4900.5. So that's the amount of energy that we have at the end. 100 times 9.81 will give us 981. So 981 times h1 is equal to 4900.5. And then dividing both sides by 981, we get pretty close to 5 meters. So h1 is equal to 5 meters. This then is the solution. This is the height that the carriage needed to start at relative to the peak of the loop-de-loop in order to completely clear this 10-meter loop-de-loop. In this video, we examined 4 sophisticated applications of the law of conservation of energy. This ends our discussion of work and energy. We're ready to move on to momentum.